That's why it's helpful to look at few common situations where technically correct optimization still produces design that are awkward from an engineer standpoint, and to show that what can be done differently to avoid these pitfalls. So the first scenario is typical for narrow veins with variable thickness. The root cause is almost always the same. The original block model was built on a grid convenient for the geologist, not for the mine designer. The block is too large relative to the average vein thickness, and as a result, even an optimizer that handles clustering and angular ranges is forced to include waste to assemble a continuous stope at all. The model that looks acceptable, plant dilution occurs, and the economic indicator is positive, but when the result moves into design, turns out that the actual mining width exceeds the allowable limit for the stope or for the mechanized cut and fill fleet by 0.7 or 1 meter. The designer naturally trims the outline back to the permitted width, and the original stope economics collapse with it. So this can be perceived as an optimization error, but the real mistake lies in model scale. The best practical approach for such ore bodies during data preparation is to switch to a finer discretization in the vein zone, use subblocking at contacts, or define the vein as a separate domain with its own grid, so the optimizer does not have to widen it by pulling in barren rock. So then both shape and economics will be closer to what can actually be mined. The second common scenario appears in stratiform, gently dipping, or otherwise well-organized deposits where the mine relies on a regular grip development pattern. In this case, the mistakes usually goes in the opposite direction. The optimization is run on standard cubic block grid without considering the mine's actual discretization. The result is an irregular stope outline that in some areas pushes into future rooms, in others cuts across plant pillars, and elsewhere carves out thin slivers that have no practical place underground. From the optimizer point of view, everything looks fine, right? So it's simply a collection of blocks with positive net value. But from the design standpoint, it's chaos. Trying to fix this after the fact does not work. The moment the engineer snaps the outline back to the mine's room and pillar spacing, much of the model economic benefit disappears. The proper workflow for these deposits is different. The first lock in the mine grid, the discretization used by the project, whether it's 15 by 15 by 3 or 20 by 20 by 4 or another scheme, and then evaluate cell economics using the same discretization. When optimization operates on the same cells that appear in the design model, integration becomes seamless instead of a geometric correction exercise. Well-structured K-mine workflows follows exactly this approach. Optimization runs on clusters aligned with the mine's grid steps rather than on isolated blocks, ensuring the outputs are immediately compatible with the real underground layouts. And finally, the third scenario appears in massive and stockwork deposits. At first glance, this seems straightforward. The ore body is large, the grade variability is moderate, big stopes are permitted, access development is relatively flexible. But yet, this is exactly where errors often emerge at the boundary between geotechnical limits and economic optimization. When the optimizer sees that adding a few marginal blocks slightly increase metal with only moderate dilution, it naturally expands the shell. In the block model, this looks like improvement, a cleaner, fuller shape, but in reality, the outward expansion may push stope into a zone where the ground control plan requires pillars, extra support, reduced stope height, and the designer is then forced to either trim the stope back or split it into two smaller rooms. Either option affects backfill volume, access length, and even the schedule. So to avoid this, the optimizer needs to interact more strictly with geotechnical constraints at stope boundaries. If there are zones of reduced stability, they should be flagged explicitly and excluded from the economic shell rather than left for correction during the later design stage. This is a classic example of how a slightly More conservative optimization leads to a smoother, faster workflow and cleaner final project. So now let's turn to what actually helps, the best practices. First, it's essential to separate zones based on data quality. If one part of the deposit has dense drilling and another is sparsely sampled, there is no reason to apply the same grid resolution or constraints to both. In well-drilled areas, you can allow finer optimization and more detailed stope shapes. In poorly drilled zones, it's better to restrict the geometry upfront to stable, easily designed forms, so you don't end up chasing questionable tongues of ore with expensive development. Second, for veins and other selective mining situations, a preliminary geometric smoothing of vein contact is often worthwhile. Instead of using a boundary that jumps from 0.8 meters to 1.4 meters every few blocks, build a smooth surface that yields more regular stope dimensions. While this may trim the theoretical maximum recovery, it usually improves mining consistency and reduces dilution, both of which tend to matter more in underground operations. And third, tight coordination between optimization and scheduling really pays off. In the first scheduling pass reveals that certain stopes don't fit due ventilation, access, or sequencing conflicts. It's better to feed those constraints back into the optimizer and rerun the model instead of manually trimming shapes afterwards. This way, both the economic and engineer outcomes emerge from a single and consistent set of constraints.